Let me know if you see my screen right now. So okay, how do we download and install Contiki? You just have to Google Contiki OS here, and the first link takes you to the official Contiki OS page, as you see it here. Now there are two developments. One is Contiki NG, so new development or next generation of Contiki, and the historical Contiki OS Git repo. You can actually see the older versions of Contiki here, and you can actually check out the next generation of Contiki, which is actually what we're gonna be doing right now. So you can check out the code, contribute on GitHub for this one. And you can see it's pretty well maintained. I mean, some of the modifications here have been done just a couple of months ago. But there's an easier way to actually install Contiki. So you can actually, of course, clone this repo and you can try to build it from source, or you can actually download a virtual machine that has everything installed for Contiki. So you can search on Contiki OS virtual machine, for example, or I think it's Instant Contiki. Instant Contiki will lead you to a SourceForge link, and this contains the latest versions of Contiki OS. You can actually choose which one to download. The latest right now here is Contiki 3.0. I've chosen Contiki 2.7. It's most downloaded and has all the applications that I'd like to show for today. So going here to Contiki 2.7, you're gonna find the zip archive with a virtual box or VMware player image that you can download. It's 2.2 gigabytes, so we're not gonna wait until this whole thing downloads. I've already downloaded in advance. And if you go, basically it's going to be a zip. If you unzip it, it's going to be the content of a virtual machine, which you can actually run on your system. If you have Windows like me here, I've used VMware Player to actually run this virtual machine. And then this is basically when it boots up, this is how it looks like. So it's a simple Linux distribution that has Contiki installed over it. So of course Contiki does not run on a PC or on a general computer. Constrained devices. So the model that we're going to adopt in developing applications with Contiki is compiling the entire operating system image and then downloading that operating system image to a certain device or a sensor node, so to speak. So go to, let's see, files here. We can browse the whole Contiki structure. So Contiki 2.7, it's got these files and folders, and you can see here, of course, different CPUs that are supported. ARMs, x80, x86, AVR, and so on. So quite a few processing architectures that have been supported by this platform, regression tools, and so on. Mostly we're going to work in this folder, so examples here, because these are applications that have been already developed by we can actually run them in this context. We can either run them physically on devices, but most of you don't have these devices, but that's okay. You can actually employ this network simulator. It's called Kuja, and you can actually deploy and run applications and test applications here even before you actually start deployment on actual devices. Unfortunately, there's no ESP32 support yet, so there's no way to actually run this on your boards. But the next week demo we're gonna do on NATEX, that's gonna be fully supported on ESP32. So for now, let's use Kuja as the simulator. And let's create a new simulation. So file new simulation, you just name it whatever you like. You have here some settings which pretty much you leave undisturbed. Radio medium for communication between different devices. You can have different types of medium or different types of simulated mediums, of course. I basically use this graph medium of distance loss, which is most common. You have a mode startup delay of 1000 milliseconds. So whenever we start the simulation, it takes 1 second to initialize everything. So you don't start immediately off the bat. And this is a random seed for the simulation. So we just hit create and it's going to open up some new windows. Now the most important window I think is the network visualization one, where you can actually see your whole network. So in this simulator you are able to simulate multiple Contiki devices running in and establishing a network and seeing network traffic and packets being exchanged and so on. So it's more than a single device simulator. You can simulate up to maybe tens or hundreds of devices in this one. So it's very powerful. Let's start with the first example here. Let's just go to modes here. Modes is sensor mode or IoT devices that we want to create, and add a new mode. So create new mode type. There are a few architectures supported here. Let's use the sky mode as an example. This is T-mode sky, I think was one of the modes that Contiki was developed on and has the most examples running for it. So sky mode, and this opens up a new window. It's got a brief description. We're going to leave it like that. And then it actually asks you for the firmware that runs on this particular device that we're going to be simulating. So we're going to have to give it the path towards an application that runs on this device. So let's go to browse here, and as we can see here, we are already in the Contiki folder for examples, and we have all the examples listed here. So let's take the simplest example ever, which is Hello World. And let's try to compile this one and see how it works. Hello World, where are you? Hello World here. Okay, so going here, we need to select the C source for this one. So if we give it a path like this, you can actually hit compile, and it's going to take a while, but afterwards it's going to compile the whole application. And whenever it's done compiling and we have no errors, we can hit create. And this window will actually ask you how many of these devices do you like to create. You can create 1, you can create 10 or 100. Let's create 1 first. And again, it's gonna ask you where to position this in the network simulation. You have some options here, but let's keep to random positioning. So add modes. And what it did right now is it created this sensor mode here in the network simulation window. You see it here, it's numbered 1. Now we can actually add some more things to the visualization. For example, you can add its address. Right now there's no network here, so the address would be 0. You can actually see the radio environment. So this is the radial range for the device, and it's simulated as a sphere in 3D or in 2D as a circle. You have the green circle, which is full connectivity range. So whatever other node is in this range, it will have 100% packet reception. So no loss, basically. And you have the gray area here, which is basically the detection range. And it doesn't guarantee that all packets will be sent to the destination without errors. So it simulates kind of like a very primitive transmission scheme of packets. It simulates a lossy network. Whenever you have a network, right now we don't have one, we only have one node. Okay, so given this, let's go to examples and see what we have compiled, what applications we have compiled actually. So hello world, and let's open up this hello world.c and see what it contains. So this is the application. Of course, you need to include contiki.h. You need to include standard io.h for printfs. So if you want to have printfs, again, fully written in C, so it's very easy for you to understand. Now, whenever you are starting a Contiki program, all Contiki programs are processes. So that within Contiki, it's executed regularly. So you can see that that piece of code being executed in a loop forever. Typically, you start processes whenever the system boots or whenever a module that contains a process is loaded into the system. So this will be the same thing that happens here. Whenever we're gonna hit the simulation button, we're gonna actually load this code at boot up, and the process will start, and it's gonna run in a loop. So you see here that you run this code in a cooperative fashion. So you can have different processes which are being defined, and if we add new processes to this code here, they're going to be run in a cooperative fashion. So one thing that I think worth mentioning is that coding Contiki can run in one of two execution contexts. So you either have a cooperative context or a preemptive context. And the code that is running the cooperative execution context is run sequentially with respect to other code in the same context. So if we define a new process here, both processes will be run sequentially. Cooperative code must run to completion before other cooperatively scheduled code can run. So you cannot have things here which are getting stuck in a while one loop, for example, because otherwise you're going to have a single thread actually preempting everything else. So when preemptive code when you put execution model for a change, then you may stop the cooperative code at any time. So it can come and it can preempt the cooperative code. And the cooperative code will not start again, will not be resumed until the preemptive code has already completed. So this is actually not very visible here, but I think it's worth mentioning that these processes, they always run in a cooperative context. So the preemptive context is used by interrupt handlers and other events, which can be actually processed by these processes and can be actually triggered, and you can actually run some pieces of code from interrupts or from other events that are from outside of the process context. So we have here a very simple process. As you can see, we actually need to actually declare it to the operating system. So we do this by this declaration here, process hello or process, and we give it a name. We start it, so we add it to an auto start processes queue. This means that whenever the operating system will boot up, we'll add this process to the other processes that are running. And you have the actual process code here. It's a very simple one. You have process begin and process end that basically guard the main part of the code that's been executed. And the main part of the code is a simple printf hello world. That's that. And this is the whole code here. Okay, now going back to Kuja, let's simulate this one and see what actually the node will print out. Now, if we want to see what the node prints out, we have to right-click on it and open serial port, because the printfs will be actually done on the serial port of the device itself. It doesn't have a display, so it does have no other way to actually print out other than a serial port. So standard IO is mapped to the serial port. So if you open it and then we hit start on the simulation control here, we're going to see that the simulation basically has started, and there are there's some printed information here about the RIME protocol. RIME protocol is for routing, and it gives automatically, it assigns an address to the node. So it's address 1 right now because there's no other node here. You can see the MAC of the device, and you can see some messages of Contiki booting up, and starting hello world process and hello world printed. So this is basically what it does. It's a very simple application to actually check everything is up and running, and this is everything it does right now. Okay, questions so far? Okay, so let's move to something more interesting. So we do have a lot of other examples here that we can use for our devices. Let's see. We can have a simple serial shell in which we can actually control and interact with the node. I think we can do this by going to Sky Shell here. So skyshell.c would be the main. Now this is a bit more complicated. Well, not so much actually. Again, you define a process called Sky Contiki shell, and you auto start it. And then you have a periodic function here that's executed as a debug timer. And this is the main process thread for the serial shell. So what you do here is you actually attach some functions to the process that will initialize different drivers in this application. So for example, you have this serial shell init, Blink init. Blink is a simple application that actually blinks some LEDs that are attached to the node. So you have 3 LEDs, I think, attached to the node, and you can actually blink them from the serial shell. And you have initializing here for different protocols. RIME is a routing protocol for the network. Power tracing, power init, these are done for functions used for power profiling of the execution of the code on the node. Yeah, let's try to run this one and see what it does. So let's remove this one. You have to delete Sky 1, and then modes, add, let's say create a new one, Sky mode, and then go to the folder that contains the serial shell example. So Sky shell and Sky shell.c. Now it's going to take a while to compile everything. And now we can create this one. Again, single node. We're not going to create a network right now. So add modes. It added the mode here. Again, we can open the serial port before actually starting the simulation. So we see what happens on the serial port, and then we hit start. And as you can see, again, it started, but right now it shows a prompt here. So I can send some commands through the serial interface. For example, if I type in help and hit send, it will, let's make this one bigger. It will actually list all the commands that are available through the serial shell within this application. So You have different commands here. You can, of course, measure the power consumption, but this is going to be simulated right now, so it's not going to be running on an actual node. You can even change the transmit power for the radio transceiver, which is attached to the node, and you can do all sorts of stuff. I think the simplest thing we can do is actually blink some LEDs. So if you blink, for example, times the LEDs, but we're not seeing the LEDs here. So let's see if we can actually open a window to. Yeah, you have this command here, show LEDs on Sky One, and this simulates how the LEDs, whether they're lit or not. So right now all LEDs are not lighting. So whenever we send this, blink 100 means that it will blink the LEDs 100 times. So you see that it does exactly that. Of course, the simulation time step is much faster than real life. So 100 LEDs blinks for just a few seconds here. And again, you can do all sorts of other stuff within this serial shell here. Okay. Let's do something more interesting. Let's simulate an entire network of these IoT devices. So just delete this one. And let's add new modes. And use a different example. So if you go to IPv6 here, we're going to find some examples with IPv6 connectivity. What we're gonna want to do is actually construct a network architecture where we have a router, a border router. This one is responsible to actually routing the traffic from the network to the internet and backwards. So this is gonna be the gateway for our entire network. So we're gonna create one node that has this RPL border. And this is let's first create this one, border router, compile it, and create. So we're gonna have one actually has this border router profile, and then let's create other nodes that do not directly connect to the internet, but they can communicate and they can establish a multi-hub network. So we will add them here. Okay. And the application is a simple one that reads some sensor data from each node and sends that sensor data to the border router. So this application is called Sky WebSense. So let's compile this one as well. And create. And we're not going to be creating one node. Let's create 4 nodes, for example. Random positioning again. Let's add them. And it automatically created this random positioned network where you have these nodes. We can drag and drop each node. So let's build let's build an architecture of a network architecture where we have so node 5 is the most remote, so to speak. Let's see, node 3 directly connects to node 1. So if I drag it and node 1 comes into the green circle, then it means that it has 100% connectivity to node 3. So it will see node 3. Node 4, for example, doesn't see node 1, but let's make it see node 3, for example. So you can connect via multi-hop, through node 3 to node 4. And then node 2, the same, you have to, let's say, drag and drop him and you can connect node 2 to node 4 and then node 2 to node 5. So what we have right now is a network in which we have kind of like, this snaking line here pattern where we have node 5 that doesn't see other nodes except node 2 doesn't see other nodes except node 4, and so on until the border router here. So let's add actually radio traffic. Okay. So whenever we start this network, if we hit start as a simulation right now, we will see radio packets being sent through this network. There aren't a lot of radio packets being sent right now because the border router is not connected to the internet. So again, we can see mode types. Yeah, so it colors them differently if they have different applications running on them. So the 4 nodes here, they have the SkySense application running on them, and node 1 has the RPL border router application running on it. Now, how do you connect this border router to the internet? Well, you can actually have a virtual, you can open a virtual tunnel to this node, to the simulation, and connect it to an actual browser. So if we, let's see, if we go right click on this node, you can open a serial socket as a server. So it says here that it's listening on port 60,001, and we have an application that we can actually run, and it will actually open this for us. So let's open a new terminal, and let's see if I go to Contiki 2.7. Examples, I think IPv6, RPL border router. So it's the same folder that we have the border router application running from, and we run this one make connect router Kuja. Okay, so what you see here is it has created a tunnel interface, and it has already connected to the node. So it sees node 1 that we are running the RPL border router application on. It sees it that's connected. So you see the IPv6 addresses of that node here. And the interesting part, okay, so we have this node right now, which has this IPv6 address. It's already allocated. So we can connect, if we go to, let's say, a browser right now, and open up a browser, internet, okay, Firefox, and connect to this node, it will hopefully, if everything runs, it will show me a web page, a very simple web page that this sensor is actually serving. So we already have it here. So if you go to this, yeah, we see the very simple web page that this application is serving us. So it sees its neighbor, and it has only one neighbor, 303, and then you see routes in the network. And unfortunately, we don't see other routes than the route to node 303. Why is that? Because, okay, let's pull this one closer, I guess. So now I can communicate and refresh the page. So we see if it, yeah, it did. So right now we see, we are in full connectivity of the network, and we actually see in the simulation that packets are flowing back and forth through the network. So we have full connectivity to all the nodes in the network, node 3, node 2, node 4, and node 5. And they're in the same arrangement that they are in the simulation. Now we can dynamically, move these nodes. So right now, if you move node 4 here, it automatically dropped out of range of node 2. So again, if we refresh this page, we should not see any more routes to node 2 or node 5. Theoretically, we will see a new neighbor to node 1, which is node 4. So let's see if that happens. Yeah, this is exactly what happens here. So we see new neighbors, but we actually also see that node 2 and node 5 are in the route. Updated the routes list. Interesting. Okay, so now another interesting thing is we cannot so only connect to the to node 1. So node 1 is serving this kind of like table with all the routes here, but we can also connect to nodes within the network that don't have internet connectivity. So only node 1 right now has internet connectivity. Everything else here is done through Contiki's routing protocol, but even so, we can connect directly from the network, from the internet, to any of these nodes here. So let's do exactly that. Let's open a new tab and let's try to connect to node 303, for example. Or node 404, for that matter. And yeah, so we connected to this one here. And node 404 will serve a simple web page in which you're going to see the, of course, simulated values for the light and the temperature sensors. And of course, if we refresh it, it's going to serve a new web page with hopefully other recordings or not. Anyway, you see that each time I refresh it, it triggers, a storm of packets within the network, and you finally get some new readings. Again, we can do this, and we can even connect to node 5, which is the most remote node in the network. Yeah, this is the address. And it will serve me a very similar web page in which we have now the readings of temperature and light from node 5. Okay. Any questions? Because I think this was all for today. So if you want to develop a new application, for example, for Contiki, we can do exactly that. But you have to, of course, write some code in C for it. So you can actually browse through these applications, and you can see, how they're implemented. IPv6. If you go here and you open the SkyWebSense app, you see the files for it. SkyWebSense.c is the main file. So you see here that it declares two processes, web demo and web server, and each of them handles different parts of the application. And of course, it's a bit more complicated than the first examples that we have run on the network, but it's basically written in C, so it's not very hard to actually follow what's happening here. Again, if you want the documentation for Contiki, you can get it from the Contiki wiki. So you have all these references for the functions that Contiki is using, and you can use them too. Actually, let's do another one. Let's try to build, let's say, our own application. So I'm going to show you how you can build a very simple application. Let's, I don't know, let's copy this hello world example. Let's rename it to process example. Okay, And let's modify this hello world application to do something a bit more than what it does right now. So let's add something more to this. You see here that the process thread, whenever it's created, it has as parameters of course, hello world process. It's a pointer to the process that we have already created. A list of events that this process is listening to and data attached to these events. So, for example, if I modify this after it prints hello world, let's say it waits for an event. So again, sorry, not really used to the keyboard on this laptop. So while 1. Let's say whenever an event comes, and we have this function that we can actually call that catches events. So it's called process wait event. So whenever an event comes, this function will actually unblock and it will execute the next line of code, which is, let's say, a printf. And we say got the event. Got event number 1. EV. Okay, so what this does is whenever this is an interrupt, for example, or some button press, you will actually see this in printed form. So let's save this one and let's compile it and add it into the simulation. Let's create a new simulation here. Remove. Okay. And add a new mode. Again, it's a sky mode. Let's go to the folder that we've already created. It's processing. And select the hello world.c. Again, you can rename these and you can probably make a better structure for your example, but for now, let's do it like this. And okay, already compiled. Let's add a node, add modes. Okay, and now let's see serial port. So basically this is gonna output on the serial port whenever an event happens. So start. Of course, hello world is started, but we don't see any event happening right now. So let's try to trigger an event. Click button on Sky One. Let's see if the button is linked to any. It's not linked to any interrupt right now. Okay, no worries. So it doesn't trigger actually an event. Okay, let's try to trigger an event then. And the way we will try to trigger an event is to actually attach an event timer. So attach a timer to the process, so whenever the timer elapses, an event will be triggered. So let's go back to our example here, and let's modify it a bit to actually have this timer initialized and to use it. So we have to, within the process thread here, we have to define a timer. Static struct timer. Okay. And we have to initialize it, of course. So after process begin, after hello world, whatever timer set. So we have to give it the let's see, pointer to the structure that you've already defined. And now we are actually setting the expiration time for our timer. So it's Contiki already has defined the clock underscore second. So this actually means 1 second in real life. But given the fact that the simulation is not running in real life, let's multiply this one by 100. So even if it's very slow in our Kuja simulation, it will happen very, very fast. And again, if you are compiling this, or if you would be compiling this on a real node, you're going to keep clock second, and it's going to trigger the timer every second. Now it's going to trigger the timer every 100 seconds. Okay, so while one process wait event, and now whenever a timer triggers, so this timer triggers once every 100 seconds, we have this function that actually checks if the timer has expired or not. So if timer expired, then we do something. We print out timer expired. Okay. And I think this only happens once. So for these timers, we have to restart them every time they expire. Restart. Okay, like so. And this will happen every time within the if. So, oops. Okay, like this. And now let's see if this works. I have to recompile everything, so I have to delete this one and add a new one. Fortunately, it does not do that dynamically. Okay, recompiled, create modes, serial. And if everything works out just fine now, it should print out. Yeah. Okay. So it prints out periodically timer expired, and it also prints the event that has been triggered by the timer. So even number 136, whatever, it's a number. Okay, so this is a very simple application that shows you, how you can actually build a process that periodically executes something in the background. Okay, questions? Okay, if not, this concludes our lecture for today. Thank you very much for attending, and see you next week.
Thank you for the presentation.
Thank you.
Thank you.
Bye.